Hey everybody, so we're basically on the very tail end of chapter 17, and then we're going to jump into chapter 18. Just reviewing the last reaction we were talking about. It was number 12. It was the Wittig reaction, or Wittig actually, I'm sorry. The Wittig reaction, we pronounce it V as in Victor. Wittig, even though it's spelled Wittig. And this is just an example of kind of how it worked. So you have like two molecules, something with phosphorus, like double bound to carbon, PPH3. So it's CH3, CH, PPH3. Those are phenols. Then you have ketones and aldehydes. And basically what happens is that the top, through a kind of nucleophilic mechanism, attacks the ketone, and then there's a little bit of mechanism, and then you get an alkene. So basically this carbon gets connected to that carbon and you make an alkene. And the byproduct is triphenylphosphine oxide. This molecule by itself, PPH3, is called triphenylphosphine. Triphenylphosphine. This is triphenylphosphine oxide. Okay. I'm not going to review every little detail of this. I'll show the mechanism though again of how the Wittig reaction works. It was in the last little bit of the last lecture. But basically, you have a ketone or aldehyde, right? Ketone or aldehyde, and then this is that Wittig reagent thing, and it's in resonance. So there's a single bond form and there's a double bond form, where like that pair of electrons kicks in. Then you have the carbon double bond form. But for the mechanism, you just want to see the single bond form with a dot negative. It attacks, just like a Grignard or something. Now you have a CC bond that you just created. O minus kind of connects to the phosphorus. You have this little four-member intermediate. That's kind of cool. Very simple four-member ring intermediate. It's called a beta-ene. I don't know. Beta and then INE is ene. So that's pronounced ene. So it's called the beta-ene intermediate. And it basically just falls apart. Two electrons go one way, two electrons go the other way. That gives you your alkene and triphenylphosphine oxide. Triphenylphosphine oxide. And yeah, that's really cool. And then I just showed kind of at the end last time, like how you could look at an alkene and propose a synthesis of it. So like this trisubstituted alkene, I could be like, well, I'm going to make that double bond in one step from piece A and piece B. Piece A in this case I'm saying is ketone. Piece B is the Wittig part, or the phosphorus part. Of course, you know, with the mechanism, you'd resonate this to show the dot negative, and it would attack, do your little beta-ene stuff, and then you'd get the alkene. Of course, the other thing that we talked about, I'm not going to review because it's in the last lecture, but how do you make these? It's really simple. It's an SN2 reaction with triphenylphosphine, PPH3, just a SN2. That attacks, kicks off the Br, and then you use this as a base, and it takes off the proton and makes the negative charged species, which you can draw in two resonance forms as this. Okay, so that's a review of the Wittig reaction that we described last time. Okay, so we have one last reaction of ketones and aldehydes from this chapter, number 13. This is a slightly weird reaction, but it's, you know, once you learn it, it's not that weird. It's an oxidation of a ketone. Oxidation of a ketone, which sounds totally crazy, and you should be blown away by that. Like, what could you oxidize a ketone to? What, a ketone seems like an unoxidizable functional group. Well, anyway, it is oxidizable, and the reaction is called a Baeyer-Villiger oxidation. I'm going to provide a kind of mini treatment of this. I'm just going to show what it is, show what the mechanism is. The book, I think, goes into a little more detail. But how can you oxidize a ketone, and what could you oxidize a ketone to? Well, if you have a ketone, it seems unoxidizable because there's like, it's at the maximum oxidation state, right? Well, anyway, this crazy reaction called the Baeyer-Villiger oxidation is an oxidation, and what it oxidizes a ketone to is an ester. An ester. How could it oxidize a ketone to an ester? That's kind of crazy, huh? Well, the way it does that is, and what the reagent is, it's a peroxy carboxylic acid. Okay, this is actually kind of what, I don't know if you remember MCPBA. Remember MCPBA? This looks like MCPBA in some ways. What is MCPBA and what did it do? Well, if I have like an alkene and I want an epoxide, remember that MCPBA was the way to do that. MCPBA. It makes alkenes into epoxides. What MCPBA is metachloro peroxy benzoic acid. So the peroxy benzoic acid is this kind of weird C-double-bond-O OH thing. It's like a funny carboxylic acid, and it's metachloro. Metachloro, right? Metachloro peroxybenzoic acid. Anyway, that's how you make epoxides. But so this is kind of like a weird MCPBA. It's just it has a CF3 instead. Okay, so how does it convert a ketone to an ester? That's pretty weird. So the way it does it, and the mechanism is, and you know what's been the general theme of this chapter? The general theme of this chapter has been that certain things add to ketones and aldehydes, right? Nucleophiles add to ketones and aldehydes. And that's what's going to happen here. But the first thing we do is rip off the proton, and that activates the ketone for attack. So, all right. We've activated the ketone for attack. And then we have a nucleophile. Let's make a guess what happens. You activated the ketone for attack. It's actually an RSCC, and I'm skipping the RSCC here just to save time. But that is ready to be attacked, so let's attack it with our O- thing. So now we're just having this attack that, and alright, nothing crazy yet, right? Okay. O, 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 CF3. Okay, so nothing too crazy happened. All we did was we activated the ketone with a proton, had the nucleophile attack, and now it's attached. Okay, and so now the kind of fun part of the mechanism is that this oxygen, maybe I'll redraw the OH to be a little more upright. There we go. Now this oxygen sees that proton and it's like, I'm going to take that proton. ... So the oxygen is kind of talking to that proton and it's going to take it. So what happens is that this takes the proton, this pair of electrons swings down and makes the double bond O. Then something kind of weird happens where this ethyl group, the ethyl group, actually jumps to the oxygen. So that's how the ester is being formed off that oxygen. And this goes there. So it's kind of a weird mechanism, and you can put it into your notes. We may or may not ask you about this mechanism. I always started with the double bond O, seeing that proton and saying, I'm going to take that proton. So it's double bond, kind of points at it and it grabs the proton, and then it's just a kind of a cyclic process. This pair of electrons goes there, the ethyl jumps with its electrons to that oxygen, electrons go upward. What does that make? Well, it makes the ester. That's how you get the ester. And then the byproduct is CF3 OH, the carboxylic acid. So now this went from a peroxy acid to a carboxylic acid. Okay, so that is the Beer-Villiger oxidation. I'll just say one last thing in passing that's kind of an interesting tidbit that I never really understood, and I don't have a good explanation for it. But if you were doing a Beer-Villiger oxidation with like a ketone like this, an unsymmetrical ketone, so it's like a ketone with a tert-butyl group and a ethyl group. Okay, and we're gonna do this Beer-Villiger oxidation, BV oxidation, with our trifluoromethyl peroxy acetic acid, which is essentially the CF3 acetyl-1-OH. The question might be, which side is going to get the oxygen? Because is the oxygen going to go kind of to the right side of the ketone or the left side of the ketone, right? That seems like a reasonable question to ask, right? Is it going to go to the hindered side, the totally sterically hindered side, or the sterically unhindered side? And yeah, I don't know. What do you think? Is hindered side or non-hindered? Most people would say the non-hindered side, right? It would be the non-hindered side. But for some reason, it actually goes for the hindered side, and the oxygen winds up on the tert-butyl side. Whoops, let's redraw. Yeah, so it actually goes to the tert-butyl side, which is a little bit weird. There's some explanations for that. You can research that if you're interested in it. It might even be on the Wikipedia page. What the theory is for why the oxygen goes to the hindered side, not to the non-hindered side. So this is the major product. Okay, cool. Okay, well that's the Beer-Villiger oxidation. That's all I'm going to say about it. And now we're going to jump to chapter 18. Okay, so we're done with chapter 17. Here's chapter 18. Now chapter 18 is kind of, yeah, it's a little, well, you know, it has to deal with ketones and aldehydes, just like chapter 17 did. But we're getting into this whole idea of enols now. It's like the proton next door to a ketone or aldehyde, and how we can form enols. There's also something called enolates. We'll talk about enolates in a bit. And a reaction called the aldol condensation. So there's a couple other little things in this chapter, but those are the main things: enols, enolates, something called the aldol condensation. So what was the general theme of chapter 17? Like, what was the theme of it, right? We did a whole bunch of little things related to ketones and aldehydes. The general theme was that a ketone or aldehyde could be attacked by a nucleophile, right? And then you'd have various things that we've seen 1,000 times now. maybe something like that. So O- nucleophile, like a Grignard, and then you protonate the O-. There were also cases where you formed things like that. That was like the imines, right? Imines, nitrogen things, primary amine reactions. We also formed things like this. What were those? Those are the enamines. So I'll just say like kind of imines, enamines. Those are things we saw. Enamines, enames. Stuff like that. We also saw things that kind of looked like maybe like this. Those are the acetals and thioacetals. We also saw final products that look like this. Remember this? How we could lose the functional group completely? I would probably say the Wolff-Kishner was one way to do it. Also with thioacetals, you could do this with what, H2 and something. H2 and rainy nickel, R-A-N-E-Y nickel. So that was like another way we could sort of accomplish this. Thioacetals with H2 rainy nickel, or the Wolff-Kishner reaction. We also saw that we could do things like this, and that was the Wittig reaction, make alkenes, right? So we learned about that. We also saw that we could turn a ketone to an ester. That was the, what was that? The last one, Baeyer-Villiger oxidation. Okay, so that was kind of the theme of chapter 17. What's the theme of chapter 18? Well, in a nutshell, the idea is that you can take a ketone or aldehyde, take off the proton with the base. This kind of creates a resonance stabilized species that looks like this. It has resonance, so of course the resonance puts electrons onto the carbon. And these things are nucleophiles, so you can imagine the lone pair attack an electrophile and attach something there. That's kind of the general theme. There's going to be a lot of twists and turns through this chapter, but in a nutshell, it's, you know, the neighboring proton can be taken off, you make this kind of thing, and then it attacks electrophiles. We've talked about enols. It's like an alkene next to an alcohol. This is not an enol because it has a O- on it, and it's a negatively. It's like a enol with a negative charge. So this is actually what we're going to call an enolate. But we're also going to talk about enols too. So remember, an enol, I'll just draw an enol. That whole idea of keto-enol tautomerism, keto tautomer, enol tautomer. Yeah, that's another topic of this chapter. Yeah, cool. All right. Okay, so I guess our first topic in chapter 18 is that, generally speaking, the acidity of ketones and aldehydes. the neighboring proton of a ketone or aldehyde. So let's just imagine like a ketone, a general ketone like acetone. That proton, how do we measure acidity? What value do we consider? pKa. So pKa is a measure of acidity, and for a ketone or aldehyde it's roughly 20. So it's not insanely acidic the way like acetic acid is acidic, or HCl or HBr. But it is moderately acidic. So this is for ketones and aldehydes. Ketones and aldehydes are roughly 20-ish or so. Whoa, I drew it wrong. So yeah, ketones, aldehydes, roughly 20. We'll say the range is about 16 to 21. But a good estimate is 20. 20 for a ketone or aldehyde. Okay. And so given the fact that it is acidic, you just got to throw in the right base. We'll talk about bases in a bit. And it just pulls off that proton. And it makes... It pulls off the proton, resonates up onto the oxygen, and that makes this species that has a double bond O and an O minus, and that is also resonance stabilized. So you got two resonance structures. For the negative charge, I usually draw out the CH2. Okay, we gave this a name a second ago. What was the name we just gave this thing? It has a name. It begins with E. It's not enol. It's enolate. Okay, so the pKa is about 16 to 21, and what does that compare to? Other species, like a carboxylic acid, for example. What's the pKa of a carboxylic acid? So you'd have to go look these up in your book. There's a pKa table, probably in chapter 2. This is about 4.5, so much more acidic, right? Low numbers are more acidic, so this is like 10 to the 16 times more acidic. This is, because this is stabilized by the oxygen. The O minus is stabilized by 2 oxygens. It's a much more acidic functional group. That's why we call it a carboxylic acid. What about an alcohol? Well, an alcohol is less acidic than a carboxylic acid, but it's more acidic than a ketone or aldehyde. So this is not the most acidic thing in the world, but we can definitely remove the proton, and then we'll find out that these things are nucleophiles. We can attack stuff with them. What other functional groups do we know? Alkynes, we know those are actually kind of acidic, right? Also, similarly acidic. Chapter 13, right? We were learning about taking terminal alkynes and ripping off the proton with NaNH2 or butyllithium. Takes off the proton. And the pKa is about 20. So it's actually kind of similar to a ketone, is an alkyne. And also remember from that chapter that if you have an alkene, alkenes are way less acidic, so it's like 45. And then of course an alkane is kind of the least acidic thing in the universe. That's about 60 or so. So generally speaking, ketone aldehyde is roughly about the same as an alkyne. Okay. So why is it acidic? Why is a ketone aldehyde acidic? The reason generally, why is any organic molecule acidic? The general explanation is the conjugate base is stabilized by resonance. Okay, that means I'll just say C above because I already drew it. C above, I mean this. Once you take off the proton, this is the conjugate base. The enolate is the conjugate base, and it is stabilized by resonance. By having this kind of resonance stabilization, that ultimately makes the proton in the parent functional group, somewhat acidic, right? This resonance stabilization. What is the incorrect thing to say? When people might ask you, why is a ketone or aldehyde acidic? What's the incorrect thing to say? The incorrect thing, and what a lot of organic students say, is resonance, 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 resonance. That's an incomplete answer. The complete answer is we'll say the resonance stabilization of the conjugate base, where the conjugate base is stabilized by resonance. It's the same thing, right? So it's not just resonance, it's specifically resonance related to the conjugate base. And the conjugate base is what you get after the proton's removed. Okay? Okay, so given that ketones and aldehydes are somewhat acidic, we'll say, let's just throw out a silly example and just say like cyclohexanone, and got a proton there. This one happens to be a little less acidic. It's about 25. I don't exactly know why, but it's something about the structure of probably the structure of the conjugate base. But we'll say 20-ish or whatever. And so given this slightly acidic proton, all you got to do is throw in the right base, and it takes it off. The base that we typically use in this chapter and maybe the next couple chapters is this stuff called LDA. LDA, might memorize that as one of our super bases. It's a super base. There's a couple other super bases, but this is a pretty super base. And it rips off the proton. I could draw that just with the bond and go, alright, rip off the proton. Now you got an enolate. And you got, what did you make when the base takes off the proton? You make its conjugate acid, which is just the amine. And the pKa of this proton is about 35. So technically, this is technically in equilibrium. All acid-base reactions are in equilibrium. And the question is, in an acid-base equilibrium, is which direction does the equilibrium go? And the answer is always towards the larger pKa. So if we go from 25 to 35, this is definitely a right-favored equilibrium. So maybe I can even draw that differently and just have a big arrow on the top, a tiny arrow on the bottom, reversible arrow. So definitely, this is a quantitative reaction. This goes to completion. We still show the equilibrium, but yeah. LDA will take off any proton next to a ketone or aldehyde, or ester, or other functional groups too. Okay, so the pKa equilibrium always goes towards the larger pKa, alright? And what can we do with this now? We make it, I said it's nucleophile. So what reactions do you know of nucleophiles? For now, I'll just say we can do an SN2 reaction. That's one thing you can do. We'll get more into that later, the different reactions you can do with these. But yeah, SN2. So now this just swings down, kicks off the bromine, and now we've just made a ketone with benzene. I was going to say pH, which would be fine too. Yeah, so this is a simple example of what kind of application could you do with this kind of acidity. Well, let's take off the proton and attack something, right? Do an SN2 reaction. We'll come back to this. We'll come back. to this. So just as an introduction, there we go. Alright, so another thing that we've seen it in chapter 13, I think, the alkyne chapter. The concept of keto, enol, tautomerism. Remember that? Keto, enol, tautomerism. We used it in the oxymercuration of alkynes. We did it in the hydroboration of alkynes. That whole idea of you have a keto tautomer and enol tautomer, and they equilibrate, right? So, example, acetone will equilibrate to its enol form. Okay, this is the keto tautomer. This is the enol tautomer. Which is the good one? Which is the favorable one? Remember, we talked about that. Generally speaking, this is the major one. There's exceptions to that. So usually this might be like 99 to 1 or something like that. One thing to know is it's a rapid equilibrium. Rapid equilibrium. It is catalyzed by acid or base, though. So if you don't have acid or base, the reaction doesn't occur. So, but you need a little bit of acid, a little bit of base. So pH above 7 or below 7, either one, but not exactly 7. Okay, and are these resonance structures? Are they the same as resonance structures? Remember resonance structures? So is it correct to say, use a resonance arrow? Yes or no? No, they're not. These are not resonance structures because you're forming sigma bonds, right? You're forming a bond from oxygen to hydrogen. You're also getting rid of the CH3 to make a CH2. So and that's not what resonance is. Resonance never has single bond formation or cleavage, right? So sigma bond breakage, we'll say. I don't know. Yeah, definitely not resonance. But it's equilibrium. There's a difference between resonance and equilibrium. Okay. So what's the mechanism of these? And as remember a couple chapters ago, I don't know if you remember the alkyne chapter, that's so long ago, we saw this, and I said, you know, someday I'm going to teach you the mechanism of this. Well, now's the day. It's really easy. You're going to wonder why I didn't ask to teach you this before, but you were much earlier in your chemistry back then. So let's do the acid-catalyzed mechanism, and then we'll do the base-catalyzed mechanism. Okay, so if we have a ketone and we want to go to the enol form, the keto to the enol tautomer, keto, enol, we're going to do H plus as an example. How do we do that? Actually, we need water also, so H2O. You could either write H plus H2O or just write H3O plus. That hydronium ion works also. So this is a pretty easy mechanism. It looks like all we're doing is forming a bond from oxygen to hydrogen, and then we're getting rid of the CH3 to make it a CH2. And that's all there is to it. So start by protonating the oxygen. Now we have a CH3. And what is H2O going to do as our mild base? Take a proton, and that causes the tautomerism. So that's a pretty simple mechanism, right? Another way to maybe draw this a little nicer is I'll actually draw the CH poking out. There we go. Maybe that looks a little better. Okay, yeah, so that's the acid-catalyzed tautomerism. And recall, you know, where did we see this again? Like if we have an alkyne, a terminal alkyne, and what was the way to turn it into a ketone? It's Markovnikov hydration of an alkyne. Was it the boron one or the mercury one? It's the, if it's Markovnikov, which is this is Markovnikov, it's the mercury one. So it's HgSO4, H2SO4, mercury sulfate, sulfuric acid. And without doing the full mechanism, you know, there's a couple steps, but the end result was you would get the enol. Aha! And then it's a tautomerism from the enol to the keto. Well, now we know how that works, and of course there's acid, that's sulfuric acid, right, H2SO4. So the conversion from the enol to the ketone is really easy, right? Okay. Okay, so let's do the base catalyzed mechanism. Of tautomerism. It's equally as simple. Okay, so if we have base like OH minus, there's always a little bit of water in there also. How can we go from the left molecule to the right molecule with base? Well, now you don't have H+, so you can't protonate the oxygen. What we can do is use the base and do what bases do, take off the proton. That's pretty easy. Okay, now what do we do? Now, how do we go from O minus to the OH, and you have water? Maybe it just grabs that proton and pushes electrons onto oxygen. So this is almost as simple as that acid-catalyzed mechanism. Okay? Alright, so and being in equilibrium, so these are equilibriums. Being in equilibrium, we have different ways we can actually measure the population of like the left molecule and the right molecule. You could even use NMR, right? Because the NMR of this has one spectrum, the NMR of this has another. We almost just use NMR integration and figure out the equilibrium and the population. So we can determine the population of the tautomers, and let's talk about that now. Okay, so let's talk about the population of the keto and enol tautomers. I mean, by population I just mean the relative amount of that versus that. Okay, so I have like cyclohexanone, and it's equilibrating to the enol. In most cases, for most ketones and aldehydes, it's definitely favored on the keto tautomer. So there's 99.99% of this, and like less than 0.01%. Some cases, definitely we have a lot more of the enol, and we'll show that in a second. Interestingly though, like even though there's so much of this and so little of this, this can be leveraged to do a reaction, because this is actually a nucleophile, and we'll see how it's, even though there's a very small population of this, since this is a nucleophile and this is basically an electrophile, right, last chapter, if we expose this to electrophiles, even though there's very little of it, it'll still react. And so that, keep that in the back of your mind, is you don't need 100% of this. All you need is a little bit, and when you give it the right electrophile, it will react, even though it's going back and forth. It will attack electrophiles. Okay. Aldehydes, like acetaldehyde, are similar. Remember, we also need the acid or base catalysis in these equilibrium reactions. A little bit of acid, a little bit of base. Okay, same with the aldehyde. And the aldehyde looks like that. Cool. And it's, I think, roughly 99% to 1% or something like that. It's like a lot of that, but very little of that. Okay? Why is keto more stable? Why is the keto tautomer more stable? Any guesses? Any guesses why the keto might be more stable than the enol? I actually wasn't too sure. I looked in our book, and the book doesn't even mention it. At least the last time I checked, the book did not mention why the keto is more stable. I have my own guess, and that is, so let's draw like cyclohexanone and the tautomerism. Okay. And my guess, oops. My guess is that the CHs, those single bonds, are the two CHs, the bond strengths are actually kind of strong, and here we only have one CH, so now we have one CH and one OH, and that these bond strengths are maybe a little bit stronger than the CH and the OH. And OH is actually kind of a weak bond. So I just think that we have stronger bonds on the left. We are trading the C double bond O for a C double bond C, but I don't know the relative strength of those bonds. But definitely the two CHs, single bonds, are actually strong bonds. And the OH is kind of a weak bond. So that's kind of my guess. There's probably a little bit more to it, why the keto is more stable. So are there any cases that you can think of where enol might be a more favorable tautomer? Like we're saying, oh yeah, keto definitely stable, enol less stable. Any cases where enol more stable? Well, there definitely are. I'll show one very clear example. What if we have like this triketone, cyclohexane trione. Okay, we have 3 ketones and 3 keto tautomers. What if they all tautomerize to the enols? Which do you think is the more stable molecule, the left or the right? The keto tautomers or the enol? Well, this is not only enol, but this is also aromatic, and so this is major because now we have aromatic stability. So that this has basically benzene. This is non-aromatic. This is aromatic. So, you know, that would be one situation. There's other situations, usually where ketones are conjugated and near each other, and then the enol forms are more favored. Okay. All right, so we're now going to talk about, you know, given what we know about ketos and enols, we're going to now give some examples of synthetic reactions, so, and mechanisms and stuff, using enols and enolates. Okay, so let's learn some cool reactions. Alright, so the first reaction is, the name of it is acid-catalyzed halogenation of a ketoneraldehyde. Acid-catalyzed halogenation of a ketoneraldehyde. Simple example, got a ketone. We're going to react it with Br2, bromine and acetic acid. So Br2 and acetic acid. And our product will be the ketone with a bromine here. I guess I'll introduce a little bit of nomenclature. When we have a ketone like this, and we're describing like the next door position and the next door position, we often use Greek letters like alpha halogenation, acid-catalyzed alpha halogenation, and alpha refers to the neighboring position. This is the alpha position. What do you think this position is called? The next door would be the beta position, right? Okay, so we'll talk about the beta position later also. But a good name for this might be acid-catalyzed alpha halogenation of ketones and aldehydes. And specifically, we're doing bromination this second. But you could do this for chlorine also. Alright, so let's start by making the enol. We got to make an enol of the ketone because the enol is nucleophilic, right? We already talked about that. What's the mechanism of enolization of a ketone? How do we make the enol? Well, if you got acid around, what did we do with acids? We protonate the ketone. And acetic acid is the proton source we're going to use. Okay, so we protonate the ketone. Now we're going to take off that alpha proton, alpha again, alpha. We're going to take off the alpha proton with our conjugate base of acetic acid, so acetate. Acetate is just acetic acid minus the proton. Takes off the proton. Alright. What does that give us? The enol. What do we say about enols? Are they nucleophilic or electrophilic? They're nucleophilic. And Br2 is an electrophile, so what do you think the nucleophile is going to do when it sees the electrophile? It attacks. Now, how does this nucleophilic enol attack Br? How do we draw that? So, you got to be kind of specific here. Start with a lone pair on oxygen, circle it, kick down, and that recreates the double bond. and then the double bond attacks, and then kicks off a Br. That is how the enol attacks an electrophile. And what does that give us? Plus charge here. Okay. And how do you think we finish off the mechanism? We have an extra proton. How are we going to get rid of the proton? A mild base takes it off. We could just say minus H plus. If you specifically care what proton or what base is taking off the proton, it's either Br minus or maybe more conjugate base from the acetate, but something removes that highly acidic proton. Okay, cool. That was easy. Interestingly, with acid-catalyzed alpha halogenation, the reaction stops at the mono halo derivative. By mono, I mean what would be the other option, like dihalo or trihalo. And by halo, I mean bromo in this case. So it stops the mono halo derivative. We don't see the dihalo derivative. And why is that? We have a cool explanation for that. So why you'll only get one halogen. Let's show another example. Okay, so remember the name of this molecule? Probably not. But this we did the names of some of the common ketones and aldehydes. It's called acetophenone. That was in the PowerPoint, but whatever. Acetophenone. Okay, and say we're doing this Br2 HOAC. What's HOAC? HOAC, that's acetic acid. That's the same as that. Acetic acid, HOAC. HOAC, right, acetic acid. Okay, so say we do this and we get our products just like we just drew. We did through the mechanism we just drew. Okay, and say that we're, maybe it wants to go to the two bromines. We're arguing that it doesn't do that, but let's pretend it does. And we'll explain why it doesn't. Okay. So if it was going to go to two bromines, that's what it would do. Okay. Remember what the mechanism was in a nutshell. This gets protonated, right? It makes the enol, and then the enol attacks bromine, right? That's what we just did up top here, right? Protonate, make an enol, attack bromine, lose a proton. So that's how the mechanism works. So say that it's going to do it again from the mono-bromo. That's the question. Is like, could it do it a second time? Alright, so say there's an equilibrium. I'm just going to tell you right now, the equilibrium is not favored but, to form the protonated ketone. We'll explain why in a second. Okay, you're making a protonated ketone. Okay. Because say it's going to go a second time. You would start with the ketone, get another proton, and we're going to make the enol, right? I'm saying that this isn't going to happen, and I need to explain that to you. Why is this unhappy? And it's not totally clear if I draw it this way, but this is an RSCC, right? Let's draw the alternate resonance structure of the RSCC now, and then you'll see why it's not happy. Okay, so these are in resonance, and you have a plus charge here, right? Okay, so this is totally unhappy. This is totally unhappy, and the reason it's totally unhappy is because the Br is pulling on electron density, right? It's a electron withdrawing group, right? It's electronegative. It's pulling and pulling and pulling on electrons, and it's seeing a plus charge next door, and the plus charge is totally an absence of electrons, right? Because these are in resonance. It's a hybrid between these two structures. When the Br is pulling on electron density and there's nothing to give, it's pulling but there's nothing to give, that's a very unhappy intermediate. So this is unhappy. You're going from the ketone to something that's very unhappy, and that's why the equilibrium is not favored. Okay? And that's why, ultimately, this doesn't happen. Why can't we... You can't go from the monobromo to the dibromo, because the way you'd have to do that is basically going through this unhappy intermediate. Okay? And so that's why you get a monobromo product. That's the explanation. We stop at the monohalo derivative. There's no, you don't go to the dibromo. Okay? Alright. But what we're going to see in a second is that if we don't use acid but we use base, so if we say we use base, when you use base it actually will go to the dihalo and maybe even trihalo derivatives, okay? It's just with the acid catalyzed version it stops the monohalogen incorporation. Okay. Okay, so we just said that acid-catalyzed alpha halogenation stops at the single halogen, right? Monobromo or whatever. However, base, if we do this with a base, and we're going to call this base mediated, it's not really catalytic in base, it's mediated by base. This is exhaustive, meaning it goes to completion. It will incorporate multiple halogen atoms. Okay, so let's do ketone. We'll do chlorine this time, and we're going to use sodium hydroxide as our base. Essentially what's going to happen is you will, and I'll show the mechanism, you will incorporate chlorine, and then it just keeps going and going until you get exhaustive chlorination at all positions. Okay, so under basic conditions it does just kind of install a bunch of these atoms. Alright, so why does it do that? Well, first how does it do it, and then why does it go all the way to the end? Alright, so let's just draw the mechanism. Base. Hydroxide is going to act as a base. What does base do to this acidic proton? Takes it. Okay. This is not an enol, right? This is not an enol. What's it called? It's called an enolate. An enolate is a enol minus a proton, so negatively charged. Okay, so then we have chlorine. Oh, this is pretty easy now. This is a nucleophile, it's an electrophile, so very simple. Attacks and kicks out chlorine. Okay, well we got our monochloro. Now the question is, why will it keep going all the way to the tetrachloro derivative? Well, if we do it again, base, we'll say B dot dot is the base here. And there's another proton. Okay, so now we're going to do it again. Okay, so in this case, I'm going to show the enolate resonance form where I just put the minus charge next to the carbon. There's two resonance forms, right? I can draw the kind of standard enolate form with the double bond, or I could just put the dot dot negative at the alpha position. In this case, I'm just going to draw it at the alpha position. For illustrative purposes. Okay. Alright, so we make this enolate. And now I'm trying to explain why it keeps going to the tetrachloro. You know, why do we get, we'll get two chlorines on one side, two chlorines on the other side. And the reasoning is if you look at this structure and we think about it and its happiness, is this a happy structure or not? Well, you got a nice electron withdrawing group. The chlorine's electron withdrawing. It's pulling and pulling and pulling on for electron density. And oh, what do we have nearby? A negative charge. So this is electronegative. It's pulling electron density towards it. And we're giving it electron density to pull. So this is actually stabilized. If we look at the previous thing with bromine, we had an unstable thing. Well, this is actually more of a stabilized kind of intermediate. So, now I'll draw the enolate, other enolate resonance form. Okay, so let's just draw the other enolate resonance form. My point though is that this is stabilized. Okay, what does the other enolate resonance form look like? Okay. This arrow, again, all this means is electron density's pulled towards chlorine. Yeah. So it's pulling on electron density towards the chlorine. So let's draw it a little nicer. And we do that with a little crossed arrow type thing. Okay, it's electronegative. So overall, this enolate is stabilized. Okay. So it's not going to just form and then return back to the starting point. It's actually going to form and be semi-stabilized. And so now it can react with chlorine to form dichloro. So we will add a second chlorine, right? And then it just keeps going and going and going and going until you get exhaustive chlorination. That's the point here, is that under base-mediated conditions it's exhaustive. Under acid-catalyzed conditions it only incorporates one bromine or chlorine, right? So if you want to put one on, you use acid here, and if you want exhaustive halogens, you would use base. Okay, so take-home message about these reactions. Normally the goal is like monobromo. And we would use acid-catalyzed conditions. And the acid we usually use is acetic acid. Okay? Occasionally, want exhaustive halogenation. And in that situation, we would use base, typically NaOH. Okay. Let's do a quick synthesis style example. Synthesis style example. What if we got a ketone? And we want to attach an alkyne next door. How are we going to do that? You know, it looks like we, well, we know that alkynes can be nucleophiles, right? Like if we had this, that could be a totally nucleophile if you took off the terminal proton on the alkyne. So assuming it was a nucleophile, you just have to react with an electrophile, right? Like maybe this with a leaving group on it, right? Like what kind of leaving groups do we know? Maybe a halogen, right? So if we had a halogen next door, then this would be actually pretty doable. But we don't have a halogen, right? But we just learned how to put halogens on ketones, right? That was our new thing. Okay, so I'm going to expedite this problem a little bit just to save time. But we also need to, I think we're going to need to protect the ketone at some point in this problem. Why don't we just start off by halogenating the ketone? Because we know how to do that. We just learned how to do it. Okay, so we want to put one bromine on there. Okay, one bromine. Do we use it? We use Br2, right? And great. That's cool. That's going to help us because then we'll all we got to do is really attack with the alkyne. But if we want to install one bromine, do we use acid catalyzed or base mediated? I'm being wishy-washy here with those words, catalyzed and mediated. Catalyzed means we're using the proton and then kind of giving it back at the end, right? Mediated means we're using the base and not giving it back. So it's base mediated means that in the mechanism that we're just using the base to do stuff. Catalyzed specifically means we're use a proton, give it the proton back. So if you look at the mechanisms, you'll see that. Anyway, do we use acid or base here to install one bromine? So if you review what we just did, of course, if you use base, you get a bunch of halogens. But on the last page, if you use acid here, you get a single halogen. So use acid here. Acetic acid. HOAC. HOAC is another abbreviation for it. Okay, so we install a single bromine. Alright, so now it's just a matter of, we want to kick that guy off with an alkyne, right? Problem is that alkynes, alkynyl anions, right, like that, with a negative, say we have that with a negative charge on it, what types of functional groups do they react with? Think back in chapter 13, right? What do those things react with? Alkynyl anions. Ketones, aldehydes, epoxides, right? Ketones, aldehydes, epoxides, and also alkyl halides, right? Well, we got a problem now because we have an alkyl halide and a ketone, right? So assuming we throw in this stuff, the alkynyl anion, is it going to attack the ketone or is it going to attack the alkyl halide, the bromide? Well, it's probably going to attack both, so it's a problem. But we're smart chemists now, and we know we can do something with the ketone to limit its reactivity, right? Even just last chapter, that we can protect it. So maybe let's just protect that ketone now. Actually, let's do, I was going to do the ethylene glycol, right? But to make it more fun, let's do the sulfur one. You know the oxygen one and you know the sulfur one. And just for fun, let's do the sulfur one. Okay, sulfur thing, and then do we add proton or something else to make the thioacetal. It's not proton, right? You have to look back in chapter 17. It's zinc chloride. Zinc chloride is the Lewis acid we use to make the thioacetal. Thioacetal. All right, sweet. And all we got to do now is kick off the Br with the alkynyl anion. So we just got to throw in essentially there we go. Right? We don't even need a second step, like a water step, because usually if we do water, it's going to protonate an oxygen, but there's no oxygen to protonate. This just does an SN2, right? So, kick off the Br, kick off the leaving group. What does that give us? I'm going to abbreviate the phenyl as pH now. I'm going to draw the alkyne kind of poking downward. Alright? Okay, so how do we finish off the reaction now? How do you deprotect a thioacetal? It's water, gives you the oxygen. And if you have to review from chapter 17, we don't use zinc for the deprotection, but we do use a different metal. It's mercury, HgCl2. So very cool little synthesis problem where we basically installed a single bromine, protected the ketone as a thioacetal, did an SN2 style attack with an alkynyl anion, and then deprotected the thioacetal with water and HgCl2. Really cool, neat, recent chemistry we learned from chapter 17. Alright, so we're pretty much at the end of this lecture. I just need to mention one last thing. We're going to see this later, and I just want to bring it up real quick. It's actually really easy. What if we need to say useful for later? So I always want to bring this up. What if we need to go from a ketone to a ketone next to an alkene? This will be super useful later. And the way we actually do this requires some of the stuff we just talked about, the bromination, the monobromination. Okay, so this is actually a very simple process. I'd like to go from an alkane to an alkene. It's not a single step. And, you know, how do you make alkenes? This is, we'll keep using our organic 1 knowledge that you forgot and everything. What was a great way to make an alkene? Well, one great way to make an alkene, if you think back from organic 1, is if we have a leaving group and then you throw in the correct base. The proton gets removed and it makes the alkene, right? It's called the E2 reaction. Remember E2? And you just got to use the right base. The right base is, for this reaction, is pyridine. It's just what everybody uses, pyridine. And it just grabs the proton, makes the alkene. It's the E2 reaction. Pyridine, of course, is just a benzene with nitrogen in it. That's what pyridine is. Okay, and then what's the great way to install a single bromine next to a ketone? We just learned it. Br2 and HOAC. Okay? Cool. So Now you know if you need to go from a ketone to this sort of alkene next to a ketone, that all you do is brominate and then eliminate with like pyridine. And we'll even give you, I'll even give you a fun name for this thing. It's called an enone. Enone, right? An enone is an alkene next to a ketone. All right. Okay, so we're done.